video shall be a huge video to summarize all these 12 videos that we have done in the previous weeks. Alright, everything that goes back to this feedback system. Okay, so I'll just go like a train and hopefully things might be cool. If you still remember bounded input, we have a bounded output. Alright, this will be good. It's because then it will be stable, because a bounded output means that you're gonna decay. Alright, if it's not bounded, you're gonna go infinity. That's the meaning of it. And we'll introduce a new term here, that is number of degree of freedom. What is it all about? Is that we design a system that only we can change plant, meaning plant has a certain transfer function. Then, if anything happens, the plant spoils, everything spoils, and that's it. Alright, which is not cool. And this is just a 1 degree of freedom, where you have only a freedom to control the plant itself. Because C and F in 1 degree of freedom is simply some constant, maybe 3, maybe this 4, something of that meaning. If it's 2 degree of freedom, instead of a transfer function only here for plant, we have a transfer function for control, which is something that we've been discussing all along for a lot of videos. If you have 3 degree of freedom, then instead of F as a constant, or normally we take it as 1, right? So in such of a case that is 3 degree of freedom, then F itself has its own transfer function also. Alright? So you have more reliance on other systems, such that if a plant fails, at least you can use other system to ensure that the plant does not fail. So this is somewhat of a control also. You're using something to control the failure of other stuff, or to control the stability or robustness of a certain stuff. So a number of degree of freedom, the higher it is, the better control your signal it is. And therefore always control, for the controller they actually use PID, which is the 2 degree of freedom. I will not go into that, but something for you to know. Knowing all of this, why do we use feedback system? If you still remember back in this particular transfer function over here, the very primitive one, this is the complementary transfer function, complementary sensitivity function. This is the S for sensitivity function and such. And these are the stuff that actually help us to use feedback system based on its benefits of using this. Or in other words, of the beauty of these parameters that we have been talking about is that with that, then feedback system is actually good to that extent, right? Because you know that S is a high pass system, T is a low pass system. If you were to operate in terms of a lower frequency, where T is somewhat not that big, but rather than it's considerably big, we can assume that S itself is somewhat very small. Alright, very small that we really want it to be, and therefore decreasing the multiple or scalar of the disturbance. So we're actually minimizing the disturbance. This is one form of a good feedback system. Alright, only feedback can do. Alright, which only feedback system or closed-loop system can do. And because of this, we are only left with the reference signal or the command response R with respect to the noise. And we were to reduce the noise, in this case, to have a good tracking. Tracking means that when you have a certain input, you track out the same output. Alright, the track. So you track the input with a good output, meaning same output with the input to a certain extent. Have a good tracking on the command response with relevance that the disturbance is low and noise is low. You can also say that, right? I think it's a better way to say that is that tracking allows a better command response to be detected, such that the disturbance and the noise are kept to its minimum, and therefore your output is what your input is. That's the meaning of that. Relates proportionally to your input, or near to your input. However, although we have T as considerably high, we cannot have it to be very very high, which is equals, if you remember that S plus T is equals to 1. Alright, if S is damn low, which is 0, then T peaks, which is 1. Alright, if that's the case happen, your plant cannot take it. Alright, and therefore we want to ensure that there is a good combination of low S and a high T. Alright, in order to ensure that the input into the plant is not that high such that it will spoil the plant, we'll talk about the control sensitivity function. Alright, relates to plant capacity, the capacity where the plant can hold. Alright, when talking about high loop gain, where loop gain means that 1 plus cp0, which is the denominator of this system over here, where we rewrite this one as simply this one, and then due to high loop gain, meaning your Nyquist plot is going to be very big of a loop, or a very big of a loop but still didn't touch -1, or some sort of that meaning. If you're talking about a super big high loop gain, then this whole thing will actually approximate to 1, and therefore we analyze in terms of how the plant will go, and this plant itself leads to the plant capacity that also will lead to the right half plane open loop zeros. You should design your operating frequency that is within safe parameters of a 10 where of plant and its initial plant. And what I mean is that when you have just set up this plant over here, just when you buy it and then you set it up, your bandwidth with a certain transfer function because your plant has a certain transfer function, right? And therefore this transfer function will lead you to have a higher bandwidth. Higher bandwidth means that you're going to operate with more frequency. Alright, more operating frequencies means that you're going to have more things to work with, and you'll be very lucrative plant, right? However, as time goes by, this plant actually have a certain wear and tear, and therefore its own bandwidth has actually came to here. Its bandwidth has came to here, and therefore your operating frequency has actually became this little amount compared to this initial one. And therefore, in order to design your system, you have to ensure that your operating frequency lies just before your bandwidth. Alright, just before your bandwidth. You may also predict that at a new when you just first implant your own plant, or you just first use your plant, you can actually operate them in a higher frequency. But subsequently, when you predict that 10 years later, you should operate your machine with a lower frequency. And these are the things, and we also state that frequency must be lower than the bandwidth. Alright, this is only for the low pass system. I mean for the high pass system, sorry. If it's for a low pass system, then this range is gonna talk about for frequency has to be between B, the current frequency, and towards infinity. Right, this is for the low pass system. But they do share the same common trend in there. You should know how to manipulate with all this stuff. Alright, therefore these are the things that is required for a good feedback system. Alright, in order to determine stability of a feedback system, look in terms of the Nyquist stability criterion, ensuring that this loop doesn't go across -1. Although Nyquist stability criterion has more into that, z equals to m plus p. I recommend you watch back if you forget what is the meaning of that. But most of the focus is focused on the margins itself. Alright, speak about gain margin. The real axis of the Nyquist plot is nearest to the -1. Alright, the distance between the real axis or of the Nyquist plot, for example, if the Nyquist plot was somewhere here, we'll talk about this point to this point. Alright, the distance between these two. And the higher the gain margin, the better it is. If you were to talk about phase margin, then we'll talk about the angle that's relative to the -1. Alright, or maybe somewhere here. Sorry, maybe somewhere here, I don't know. The -1, which is the angle between the -1 and your Nyquist plot that touches its -1 point. In other words, in this -1 unit circle. So the larger the phase angle, the better it is. Alright, and we also talk about vector margin, where the distance between your closest Nyquist plot to the -1 point is simply your 1 plus cp0, or we can call this the vector margin Sm. Alright, the modulus margin, let's say. These are the stuff that mainly focus on the controller side of the thing, while the plant, the only thing that you're going to concern with the plant is still going back to the plant capacity understanding. Alright, so please remember that while the controller are talking about stability and things like that, the gain margin, phase margin, and stuff like this. All these margins that we're talking about gives rise, to a certain extent, give rise to the understanding of the Doyle stability criterion, where the difference between the perturb, alright, if you remember, L is the perturb of L naught. For example, L naught itself is when you at first you set up the certain transfer function or set up the machine when it's a brand new machine. Alright, at a long time you're gonna have a perturb, meaning due to certain wear and tear whatsoever, environmental issues, you actually grow and grow and grow and grow. Eventually you may also grow towards -1, crossing -1, alright, which is something that we need to measure. And in order to do that, we use the Doyle stability criterion to do that by simply taking the difference between two curves compared to the -1 to L naught, alright, which is 1 plus Cp naught, the vector margin of the L naught, because this is the distance, because this is the newest machine ever. So the newest machine ever is the best margin ever compared to -1, and as time goes by, your machine is going to go lousier and lousier, and therefore this loop is going to be bigger and bigger. Alright, and the Doyle's margin states that the difference between the two curves, alright, L minus L naught, must be smaller than 1 plus Cp naught. Otherwise, for this case, then it will be this thing. So therefore it's unstable. So we have to make things stable, this must be applied. And because of certain understanding that make things bounded, we're gonna divide everything by L naught. In fact, this is L naught also. And we'll do everything at the end of the day. W1 must be smaller than 1 over T naught. Alright, this is somewhat 1 over T naught, while W1 is certain functions regarding this relationship. Alright, the distance. If the distance is larger than that, then it's considered unstable. Alright, this keeps talking about the vector margin, or 1 plus Cp, or the 1 plus L, if we were to talk about it. Alright, about the inverse. If it's equals to 1 plus 1 over L naught, then you, instead of having this thing over here, you're gonna have W2 larger than, has to be smaller than 1 over X naught. Alright, this is for the inverse case. Alright, same thing but in a different formula. Alright, you need to take note of that. What have been discussed is all about the stability of a feedback system. Still coming back to this feedback system. If you want to talk about performance of the feedback system, you're going to talk about S plus T is equals to 1, the relationship. Because the S, as you know, is a high pass system, T is a low pass system. If we input a low frequency in this case, then S is low, T is high. Alright, then T is the dominant system. They call this robust in T. Robust in T is good because you have a good tracking, because you track the command response, right? If you still remember this equation, if S is down, then T is gonna have good tracking because is in terms of the response itself, FR. Where if you still don't know what the hell is command response, is actually this one over here. Because when you cover up D and when you cover up N, what you're left with is this equation, TFR. And then if you were to bring this R down, which is Y over R, is equals to TF. And this is your number of the command response type of stuff. Alright, if you're talking about high frequency in this case, then S is going to be increased, then T is going to decrease. And therefore we're going to talk about robust in S. Alright, because robust in S is going to give you very big disturbance that you can't track the good command response. This is why we often aren't much pleased to see high S. So therefore we want S plus M. We know that T mustn't be high because of plant capacity, and therefore S plus T has to be equal to 1 optimally, where T operates in the safe zone of the plant capacity while S is minimally capped. Alright, and therefore talk about the crossover of S and T. To combine T and S in the both plot, you actually create a good signal, a good output signal that is pretty much stable, alright, or good tracking all along. Alright, and that's pretty nice. If either one of T or S is going to increase, then you're going to perturb the whole system up. Alright, over here you're going to go spike. And these perturbations, how do we talk about perturbations then? Talking about this, if we have a system of L0 and as time goes by, you're going to perturb this system all along like this. You're going to change the transfer function and it will become more and more stable, or you may also go back to its stability. Alright, things like that. So you actually go within this parameter or higher. So you'll become bigger, you'll become smaller, so it's somewhat elastic to a certain extent. You become like this and then you come back to red color one, and then you go back to the blue color one, and things like that. So these perturbations keep going on if you're talking about this relationship all goes back to high frequency and low frequency again, and the transfer function itself, which all links back to your Planck capacity. Alright? For this all gonna go back to bounded input and bounded output, because you actually bound your set. Maybe this is the worst case scenario that you can ever have. So you state that this particular equation that governs this thing over here, your worst case scenario comparatively to the initial plant itself. So this region over here is your bounded region. But either you move here or you move here, it's all on you. And moving here and moving here is talking about loop shaping, because you're shaping your loop gain. Alright, shaping this whole thing is your loop gain. Alright, this is actually CP or CP0 in other words, or equals to L0. This whole thing is just your loop gain itself. So if you were to change your loop gain of its shape or its perturbation size by this, you're talking about loop shaping. This is in fact loop shaping, and you loop shape such that your output over here, alright, is bounded still, alright, within the captivative portion of what we have said. This is for the gain system, and this is for the phase system. Alright, for the phase you actually bound it over here also. You actually bound it within these parameters, and this is the allowable phase functions you want. All of this that we have been talking all along for the previous videos are talking about the feedback system, and is often looping around and end up going back to the same point, bounded input and bounded output. So therefore, this is it. I hope that this can fairly be useful to whatever it is. I shall see you soon.